The theoretical value of AIC, or the intrinsic centrifugal interdimensional acceleration, can be determined based on knowing the velocity of expansion. And this can be derived by knowing that the expansion rate across the entire universe is, in relative measures, also preserved locally, as you remember the series of light clocks stretched in a row. So what we can so basically we know that the velocity across the entire universe can be, from our observer to the beginning of the universe, can be expressed. We've determined the value of k, and we have the velocity of expansion, and we end up that the velocity across the entire universe would be 2/3 times the speed of light. Well, knowing this now allows this velocity of expansion, that this is velocity from the observer across the entire universe, allows us to just determine it across a distance. And so here we have a little bit lower, where we have it across dO, which is c times the age of the universe, and we get our velocity, or our locally measured rate of expansion, or HO, Hubble constant, and which will we get to be 2/3 divided by the age of the universe. So we get a fundamental measurement of the velocity of expansion per dO based on theoretical measures. And adding these, we can also instead of having it a velocity per distance, like when we look at a Hubble constant, we say, well, it's the rate of expansion is across a certain distance. We can also say that it's also over a period of time. And so I call this HO, and then the T. So this is the velocity of expansion per a certain amount of time, which is, here we have the age of the universe. This is velocity expansion across the age of the universe. And again, because intervals of time and distance maintain their proportional relationships in this model, we can then have this velocity expansion per measure of time locally. And then and this expression here is the same expression that was derived earlier for determining the velocity, the AIC. And so we get AIC based on fundamental theoretical assumptions of the model, 2/3 times the speed of light divided by the age of the universe. And then let's see, we now, and then come down to the end here, we put some real units inside it. We can have it where AIC, we'll have to include the 1/2 because of the projection between four-dimensional space to along in a one-dimensional direction. So we end up with AICO, which is now 1/2, based on a universe that's 10 to the 9th years old. We end up with a measure of 3.17 times 10 to the minus 10 meters per second squared. So there's this intrinsic deceleration resisting the expansion of space, as based on as described by fundamental measures. And now, when we consider this, so now this acceleration comes and fits nicely explaining the spiral rotation rates of galaxies. But it's also important to determine the location of galaxies, because galaxies themselves are being carried by the expansion of space, and they would experience this deceleration that would pull them in, contract all the galaxies in. And this is the process that finally gives us somewhat of a correlation to the mainstream model. But there's something about this issue, okay, and it has to do with, before going into this application to galaxies, we have to look at, consider inertia. Now, galaxies have inertia, and in this model, the property of inertia would be greater in the past because the velocity along the unobserved dimension was greater, and that it directly correlates to the property of inertia. So, if the property of inertia was greater in the past, galaxies would resist this acceleration more powerfully in the past than they do presently. So, for example, if the inertia of the galaxy was twice as much as it is in the past as it is in the present, then the actual motion and the response of the galaxies to this intrinsic resistance to expansion would be half as great. Inertia is greater, less response to the acceleration. If I have a car and it's a certain powerful engine and it if I put a lot of people in it, it accelerates much slower than as if it has no people in it or just one driver in it. Its response or acceleration or its motion decreases. Its response to the acceleration is influenced by the inertia of the galaxies. So this results in what I call the logarithmic or natural log functions, because now when we have to consider response, I derive, and this formulas get to be a little much, but anyways, where the distance, we're taking, integrating. We know what the acceleration of the objects would be in actual motion after incorporating the effect of increased inertia. We know that velocity, by integrating it, we would get the velocity, and integrating again, we would have a measure of the distance. And then there are some constants that get introduced, but we can figure those out by boundary conditions, such as the initial separation. And then what's interesting would be to compare the accelerations of one with the inertial effects are considered, and those in which just the so just a regular expansion of space relationship. So the expansion of space is actually conforming in terms of general forms of the functions very closely to the same, even though it's a logarithmic relationship, much different. Here we have today the 4/3, and here we have just varying linearly. The relationships are fairly close. And over here, and I should have probably have done this much earlier, this basically shows why the 2/3 powers, the 2/3 factor is derived. Here we have the distance measures over, that's distance ratios described over measures of time. So initially 2 points connected together are presently separated after the evolution of the universe this far apart, if they follow this expansion. And then if we follow this plot, we can see that if it's linear, this would be the relationship. It was 1 over h, and then we can see that it's actually 2/3. The distance is 2/3 to 1 over h. So it's a pretty, anyways, it reconfirms the 2/3, what I call. Now, this 2/3 model is also the same model that you would expect in general relativity. If objects, if they were expanding initially close together, and they were moving away, and the rate of expansion would be slowed by the gravitational interaction, the anticipated result that you would get using general relativity, that this would be the motion or the location, the distance locations over time of the objects between each other. And so I call this the 2/3 model. So when you use the simplest version of general relativity, the age of the universe, where there's no dark matter, no dark energy, just general expansion determined by gravitational interaction, the age of the universe would be 2/3 1 divided by HO, which is interesting that the general relativity in its most simplest application conforms to the model, to the rate of expansion defined by the model itself. So yeah, here I say that's the 2/3. And I mentioned some reference links where you can find it on the internet, the same thing. Okay. Now what I'm beginning to do is the variation of the proposed model from the 2/3 model, and you can see that the relationships are fairly close. That the difference, the locations of a galaxy is, like here would be the present, and as we go further back in the past, how much of a difference is there in variation? It actually would be less than this because expansion comes at a cost. And then here it is, the relationships of the 2/3 model compared to the ln, the log functions, and seeing here we have the present. So we can see the correlation is very close. That the expected locations of predicted by this model where galaxies would be in a course of time corresponds very closely to the 2/3 model, which is, and this is unitized, where C times DO. And then, okay, let's see. Now, one consequence of this, though, when we go through the relationships, we result what I call an offset model. Okay. And what we have is this would be the geometric expansion of space. Remember, as everything would, all proportional measures would keep their proportional measurement relationships over time. So if we would go back and past 2 points that are now as far apart as they can be in the observable universe would be connected together at the beginning of time. But if we mark the locations of where galaxies would be, knowing their present rate of expansion correlates to what we see now and also conforms to the velocity of expansion now, we would see that galaxies themselves enter the universe when the universe is about 1/3 its present age. So this is kind of interesting. What we have is a condition in which the universe starts off as a highly dense region of space-time, and then when corresponding to a historical location of 1/3 the age of the universe, galaxies begin to appear in this model. Galaxies are not in existence, and they are not located within a central located mass of singularity. Instead, galaxies are distributed within a region of space when the universe was basically 1/3 its present size, as we observe now. And matter streams into the core of these galaxies, which will be discussed in the future. And so the galaxies enter the universe when the universe was 1/3 its present size. They enter in with a distribution across the universe, and they do so a little bit over time. And they don't all appear all at once. There's a period of time where these enter in, and which solves a lot of other issues, such as, well, anyway, well, here's more of an example where I describe physically how this is. Here we have our present location, here we have distribution of galaxies as we would see now locally, but if we look in the past, we would see our distribution of galaxies, and they would follow along like this. Now, one of the issues that's been always kind of puzzling is why don't we see high redshift quasars? Now, quasars are observed, let's say 100 to 1,000 times brighter than galaxies, and they are correlated to very young galaxies. And most of them, we don't see any locally. They're all far off in the past, all these quasars. And since they're so bright, one would think that these would be the farthest objects you can see. But it's not. There are galaxies that have a higher redshift, and we don't see any quasars. So where are the high redshift quasars? If quasars are associated with very young galaxies, and we can see kind of mature galaxies with higher redshifts, why don't we see quasars with higher redshifts? Well, this has to do with the evolution. All the galaxies, most of them primarily start in this additional state, but as they continue to enter in, some of them will enter in at locations farther away than 1/3 the age of the universe in their historical location, and some of them will enter in closer to our present location. So this will introduce a variation. All the quasars tend to be distributed within a very tight, fairly tight cluster once you add in, consider their motion and stuff and expansion, and also how they enter in the universe over the course of time. And then we can see, this explains why we see those galaxies that start off much further away and has taken time to evolve, they'll end up being anyways, that explains why we don't see high redshift quasars, because we're getting a chance to observe in a different location and time. Let's see here. Okay, let's discuss that a little bit more. Here's a summary of some of the equations. Okay, well that's a quick run through of the general, all the formulas in the model. Well, I got a little dirty there. And that's that for now.